Continuing with chapter 2, we're still going to look at functions, but we're going to look at the graphs of functions and discuss some properties of graphs. So what we're going to first start with is increasing, decreasing, and constant functions, or increasing and decreasing constant intervals. So we'll talk about some of this and then we'll do a demonstration. So informally, on a given interval, if the graph of the function rises from the left and to the right, like this, it is said to be increasing on that given interval in which it's going up like this. So for between A and B, it's increasing from A to B. If it is, if the graph drops going left to right, it's said to be decreasing. So if it got here, but then it started doing this to C, so from B and C, it's decreasing. If the function values stay the same going left to right, so when we're talking about function values, we're talking about y values. So when we say function values, that means y. So if it stays even going left or constant going left to right, it means there'll be a straight horizontal line. That's when it's going to be constant. So what we see here going left to right, our function values increase for increasing, function values decrease for decreasing, and function values stay constant for constant. So remember, y values is the same thing as saying function values. So the intervals that we're talking about, so when we were talking about domain and range, we had intervals of x and intervals of y. Here, the only thing that we're talking about as far as an interval is it's just the interval of y values. Or just x values. I think I said y by accident. So here your interval should just be x values. So for the most part, if you're asked for an interval in algebra, you're usually asked for an interval of x values. The only time really you're asked for an interval of y values is when you're looking for a range. So this is a definition that is a little closer to what you would see going into calculus. So a function is said to be increasing on an open interval. So we're going to use open intervals, and we'll explain that when we do our example. But we're going to be increasing on an open interval y. So we're increasing. So we got A to B. And as we see, we're going up. So for all A and B in the interval, we see that A is here. So A is less than B. So A less than B implies, well, let's see what happens here. So if you look at your y values or your f values, so your f of A, f of B, if A is smaller than B and is increasing, well, that means that f of A should be smaller than f of B. So if you're on an increasing interval, if A is less than B, that implies that f of A is less than f of B. Now for decreasing on an open interval, we're going to still have that A is less than B. But what we see here is now that we're decreasing, so our line is going down. For that to happen, that means f of A has to be greater than f of B. So my function values are decreasing. So if f is less than B, this implies, or sorry, if your function is decreasing on an open interval, A is less than B implies that f of A is greater than f of B. So just to say again, A is less than B, the function values should follow. So f of A is less than f of B. So these f values are your function values. Decreasing, if A is less than B, then f of A should be greater than f of B. Your function values are going down as x values increase. If a function is said to be constant on an open interval I, for all I and B in that interval, what we should see is that it doesn't matter if A is less than B, B is greater than A, or less than A, any of that. If we're constant on that interval, f of A should be equal to f of B. So my function value stays constant. So we'll explain an open interval here and why we need one. So when we talk about an open interval, What we're saying is that we'll have an x value stuck between a and b. It can't equal a, it cannot equal b, it is stuck exactly in between. So it's an open interval because it goes back to the idea of open points. So when we say it's open, it means we approach it, but we don't touch it. Another way we can write that, so instead of using the inequality notation, if we use the the interval notation, there we go, it will be parentheses a, parentheses b. So you should not have closed points. So you have no closed points when finding increasing, decreasing, and constant intervals. So I got something in my way on my screen. All right, so we'll do a color code it. So we're going to do increasing intervals here. And then let's use bright red for decreasing. And we'll use green for constant. So we see when we start here, we start at -1. We see that right here, function values are increasing. So from -1 to 1, we're increasing. So my x values are going to be between -1 and 1, are all increasing on that interval. So we see after that what happens, we hit that -1 and my function values start to fall. So bear in mind, a lot of people want to stop here when it crosses the x-axis, but it's still decreasing after that, right? So it keeps decreasing until I get to here. So I get to 4. So between 1 and 4, it's decreasing. So this is why we have an open interval, because right at that point at 1, we see that it was increasing on one side, but decreasing on the other side. So we can't really say that at 1, it's increasing or decreasing because it's kind of part of both intervals. So we just leave it open. We say that basically coming up to that 1, if I'm coming up from the left, I come up to it and I'm increasing that entire time. And then once I hit it on the other side, I start decreasing after that. So we just leave it open. And points like this, similar kind of logic is that I don't know what's happening on the other side. So I don't know what's happening over here on this side of the -1. So I can't say it was still increasing or decreasing or constant over there. We don't know what it is. It's undefined. There's nothing there. So we just leave it open as well. So we leave it open because we don't know what's happening at the endpoints of the intervals. Anyways, after we hit 4, we start increasing again. So we're increasing from 4 to 5. After we hit 5, we see that we level out and we're just constant. So x values are going to be constant from 5 to 7. So we're increasing on -1 to 1 and 4 to 5, decreasing on 1 to 4, and constant on 5 to 7. And as you see, it's all x values. If I use interval notation here, we would say parentheses -1 comma parentheses 1. We use this u for union to say then also the other part of this is going to be from 4 to 5. Decreasing, we only had one interval to worry about, so it's just 1 to 4. Constant, we only have one interval to worry about, so it's just 5 to 7. Okay, so that's, like I said, just going back to the open interval again, that we just don't know what's happening at these little points here. So every place that there's a point, I know that it's increasing on this side of 1, decreasing on this side. So where do I say that 1 belongs to? There's no rule saying I have to pick one or the other, so we just leave it open. Same thing at the endpoints here. I only know what's happening up to one side of that endpoint, and the other side is undefined for me. So I just leave that open as well. So for your worksheet on number 1, so remember you're using all open intervals. So you can use the X values and then use interval notation. That's what I'm going to do. So I'm going to do a inequality and an interval notation. So you can do either, but I'm going to do both for us. But I want you to tell me where this is increasing, decreasing, and constant. So take a moment, work on that, and come back. And then do it one more time for worksheet number 2. So just as a reminder, a function doesn't have to have an increasing, decreasing, and constant interval. It could have just only one of those intervals. It could have 2 of them. It can have all 3. Okay, so coming back to this. So decreasing. We see that from here to here, let me get my arrows for this. From here to here, so from -5, X values, right? From -5 to 0, it was decreasing. And then we're decreasing here after, well, let's say that's what, 5, 6, 7, we'll say about 7. So what we would say is that it's going to be decreasing, like I said, from this -5 to 0. And we see it's decreasing again after we hit, oh, sorry, we didn't want the 7. After we hit the 6. So after 6, as an X value, right, it starts decreasing again. And here it keeps decreasing from 6 to, well, where does that keep going? Well, to infinity. So because you see lazy graphs like this a lot lately because of, partly because of Desmos, if you see your graph run, if your line run off the the graph, we assume it is heading towards infinity or negative infinity. So it's the X values, right? The Y values are negative infinity, but the X values keep on going forever. Another way to write that is -5 to 0, union 6 to infinity. Actually, let me fix this part because we wouldn't write this infinity here. We just say that X is greater than 6. So in the interval between X values between -5 and 0, it is decreasing. And on the interval that's everything greater than X is equal to 6, it's also increasing. I tend to like this notation better. And your book for the most part. Increasing. So we're only increasing in one place. We're only increasing on this interval. So from 0 to that 6, we were increasing. So between an X value of 0 to 6, we're increasing, or we would say parentheses 0, comma 6 parentheses. And then constant, the only place we are constant is right here at the beginning. So here, because we clearly see we don't run off the graph, we're assuming we're stopping here at this -10. If you did a little differently, that's fine. But in this case, we have my X is between -10 and -5. And if you said it ran off to negative infinity instead of to -10, that's okay. Like I said, I'm just showing you how you're supposed to read these graphs that we get like this very frequently nowadays that don't actually have arrows at the end. If it stops before the edge of the XY plane that's visible, we assume it stops. If it keeps on going like it happens here at the other end, then we assume it's going towards infinity. So part of why this graph's in here, just to explain the bad graphs you'll see when you're trying to look around at things. So here, we actually don't have one of the intervals. We're decreasing. So we start here. There's this arrow, right? So it's telling me I'm looking at x values, right? So this is saying that this kept going like this, right? So starting somewhere over here, going this direction, we see that the function values are declining. So they're going down. So as x values increase, y values go down. So this starts at x is equal to negative infinity. And it's going to end here at 1. And I'll write it the other way here in a second. Then we see it's going to be decreasing again because after that point it increases, right? Increases from 1 to 3. Then it decreases again from 3 to 4. So we do u there, decreasing 3 to 4. And then u, because it starts increasing again. And we see it's going like this, right? So x values are going this way, but y values are increasing. So as x value heads towards infinity. And there's no place that it is constant. So just to rewrite this again, if we were just to use intervals, we have x is less than 1 and x is between 3 and 4. Here for increasing, we would have x is between 1 and 3. And we have x values that are going to be greater than 4, or also the interval where it's increasing. So we also have what we call a relative minimum and a relative maximum. So this goes back to where you're increasing and decreasing again. So only places you have relative minimums and maximums are places where you change from increasing to decreasing or decreasing to increasing. So a function f of a is a relative maximum if of f if there exists an open interval containing a such that f of a is greater than f of x for all x that are not a on the open interval. Basically what that's saying, here's my relative maximum. So we're going to have my a f of a. That's my maximum. What all this is saying is that, remember, you got y's here, right? And these are your x's. So we're saying that there's a small little spot for its relative minimum. So it's not the biggest, necessarily the biggest in the whole area. It's in this little open interval. So there exists an open interval containing a. So this little red spot, this is an interval that contains a, right? Because a is here, and then there's some value here, x value here. So a range of x values, a is in there. We have a relative maximum at a if f of a, so the function value of a, is the largest value we have in that interval. And it should be, because as we see, everything here should be smaller than it. So we're just saying that if a is the relative, or the relative maximums at a, then f of a has to be the largest at y value, the largest function value. Now when we talk about a relative minimum, like we see here, we're going to have that at b, f of b. So we can talk about the other point. Once again, there's a little interval around this that contains b. So b is here, but there's a little interval. So a function value f of b is a relative minimum if there exists, right, again, if the, relative minimum f, if there exists an open interval containing b, which we have here, so f, interval of x values containing b, such that the function value at b is going to be less than all my other function values on that interval. So the word local is sometimes used to describe a relative minimum or maximum. So sometimes you might hear a local minimum or a local maximum. We also use the term extrema when we're talking about minimums and maximums. So you might also hear relative extrema or relative or local extrema. But all we're saying is that this is not the minimum or maximum across the entire function. It's just in a small little area. So relative to the points around it, f of a is a maximum. Relative to the points around it, f of b is a maximum. So another way to describe a relative extrema is as follows. So this definition is, I like it a little better and it's a little more on point, which you're going to see once again in calculus. So location of a relative minimum is the point where the function changes from increasing to decreasing. So this is my function here, right? This is my minimum. Occurs at this spot, b f of b. What we see here is that I'm decreasing on this side, and then I start increasing on this side. We see here where we would have a maximum. So a f of a. This is the location of a relative maximum is a point where the function changes from increasing to decreasing. So another thing to point out here is that when we talk about the location of extrema refers to the x value. When we talk about the minimum or maximum, the minimum and maximum is going to refer to the function value or the y value. Sorry, refers, not references. This refers to the y values, or you can say function values. So usually when you're asked for a maximum or minimum, what you're really being asked for is your function value at a point or at the location of the extrema. The location is going to refer to your x values. So a function can have multiple minimums or maximums, or only a minimum or only a maximum, or it might not have a relative extrema at all. So if you had something that was a constant function, that has no relative extrema at all. If you have something that does this, there's no relative extrema. So some of them don't have extrema. We see here, we just have one minimum. Here we see you have a minimum and a maximum. And here we see that we have two minimums and one maximum. So for this example, we just want to identify the relative minimum, the relative maximum, or minima or maxima, meaning if we have multiple of them, we don't know, for the graph of f. So we're calling this the graph of f because this is a function that is some sort of fx function. And what we see here is that we will have a minimum right here. So the minimum, we have a minimum of, we need that y value, and we see that is going to be the -10. So we have a minimum, not 4, we have a minimum of -10 at 1. So this is my y, this is my x. So we have a maximum, the value of the maximum right here is going to be +10. So we have a maximum of +10, and this occurs at -1. So my y value is +10, at an x value of -1. So like I said, when you're trying to name the minimum or maximum, that's a y value, and then the location is your x. So we have a minimum of -10 at 1 and a maximum of +10 at -1. So worksheet number 3, take a moment here. So I have this set up. So you tell me it's a minimum or maximum, and you tell me what it is, and then ask for t, so your location. So it's asking, like I said, for that, instead of an x, it's going to be t this time. So we're just talking about the independent variable. And then one more time, right here, we're going to identify any relative minimum or maximum. You're going to tell me the function value. So the relative minimum or maximum is the function value at, so we're assuming this is t again, this could be x. But when we're talking about that location, we're talking about your independent variable. All right, so we see here, where do I go from decreasing to increasing? We go from increasing to decreasing here, and we go from decreasing to increasing here. So these are my 3 extrema. So if we start with the first one, we have a relative, because they were going from decreasing to increasing, we have a relative minimum. The relative minimum is the y value. So the minimum is -1, but occurs at t is equal to 1. Here we have a relative maximum, because we go from increasing to decreasing. So we have relative maximum is going to be a y value of, we'll say that's 1's really close. So the y value is 1, and this occurs at the t value, or your x value, it's my t value of 3. My last one here is we go from decreasing to increasing, so it's a relative minimum again. The value of that minimum is approximately, so if you were close to like 0.5, that's about where it is. So I've had like 0.5 to 0.7 is usually the answer I get on this, but we see that this occurs at 4. So just to point it out, it is possible that you could have a relative minimum that has a larger function value than a relative maximum. If you had something like this minimum here would be greater than this maximum. So don't think that you have to make sure that all your minimums are less than your maximums or anything like that. You're just looking relative to this little area, like I circled here. I'm only concerned about this little area, what's the minimum or maximum. So for for 4, we have a function value, we have a independent variable of t, so we're looking at this function would be considered f of t. It's a function in terms of t, or a function of t, however you want to say that. And what we have here is, you look like there's 3 points. So remember, this is why I give you this other definition of a minimum or maximum. A minimum or maximum is where you change from increasing to decreasing, or decreasing to increasing. This is not an extrema, because it's constant on one side, but decreasing on the other. So actually at this point, we have other function values on a little interval. Doesn't matter what that interval is. There are going to be other function values that are going to be equal to what happens at this point. So there isn't truly a maximum there, or truly a minimum. Here, well, we know that's a minimum, and we know this is a maximum. So I have a relative minimum is, so the function value at this point is, we see -1, -2, -3, and it occurs at t is equal to 0. We have a relative maximum is going to be right here. And this is, let's get 4. So the y value is 4, your dependent variable is 4, or you can say your function value is 4. And this occurs when t is equal to 6. So another way you could talk about this relative minimum would be, this is f of 0 equals -3 is the minimum, or you can say that f of 6 is equal to 4 is my maximum. We know that's the location, and we know that's the actual minimum. We know this is the location, and that's the actual maximum.